if you guys can remember way back to Wednesday and before break, it was a while ago. What we did that Wednesday is we started off by reading page 13, which some of you may have actually ripped out and not kept. So that's why I asked you to open up to 15 instead. So if you remember, we read page 13, and what we did was we defined the concepts over here on page 15. And what I had mentioned on Wednesday is that when we come back today, I told you we were going to kind of ease back into learning, and we're going to do that by playing with some Play-Doh today. So hopefully it's a little more fun than your average class that you got going on. But before we go ahead, I want to make sure that everybody has these definitions in their packet here on page 15. So we're going to start off with principle of original horizontality. Actually, you know what? Let's do this all together. I'm changing what I want. This was kind of, let's get together. Do you guys want to work in partners or alone on this? Or a little bit of both? How about this? Get in a partner if you want a partner. Stay by yourself if you want to stay by yourself. Go. If you're staying by yourself, you're going to need to come grab another color Play-Doh though. So if you're by yourself, come grab another color. Hopefully your partner and you have contrasting colors to start with. So hopefully they don't match perfectly. If they do, somebody's going to have to grab a different color Play-Doh today. Did you take the black on me? You did. Okay. All right. So what we're going to be doing with our Play-Doh is demonstrating, we're going to basically pretend your Play-Doh is rocks, and you're going to be making some you're going to be making these concepts. So we're going to start off with the principle of original horizontality. You guys should already have this defined. This is the packet that we used. We said that principle of original horizontality says that sedimentary rock layers are always deposited in horizontal layers. Any movement happened after deposition. So what I'd like you to do with your different color Play-Dohs, the reason you have different color Play-Dohs, they're supposed to be representing two different kinds of rocks. I would like you to see if you can demonstrate with your Play-Doh this principle of original horizontality, that rocks are deposited in horizontal layers. And any movement that happens to those layers happens after deposition. See if you can put together with your Play-Doh how this might happen. I'm going to give you a few minutes to kind of just brainstorm on your own first before we go ahead and do this together. Phoenix, either go join a group or grab two colored Play-Dohs. I just called you Phoenix, but I mean Remy. Yeah. Remember, you're both named Phoenix or both named Remy in my brain. Yeah, you can join Alex or join. See if you can demonstrate that. Horizontal layers. Any movement happens afterwards. Pretend the Play-Doh are rocks and make some gorgeous examples of this for me, would you? You're partly there. Now you have different color rocks for a reason. Oh man. Imaginations. Come on, use your imaginations. You guys got this. Oh, we're confused. Let's start from the beginning. So we got sedimentary rocks. Who remembers how sedimentary rocks are formed? Yeah, it is. And if you don't remember how sedimentary rocks are formed, remember we have a reference table for that. So sedimentary rocks, I just grabbed the rock chart. To figure out how sedimentary rocks are formed, we find this rock chart. Read it backwards. It happens when sediments get deposited, buried, compacted, and cemented together. How can I demonstrate sediments being deposited? Let's start there. I literally am going to take some sediments and I'm going to toss them. There are some sediments being deposited. No, you might not have done it wrong in the end. Then what's going to happen to these sediments? They're what? They're going to get deposited, buried, compacted, cemented together, or like Jenna said, they're going to get flattened together. So these sediments are going to get squished together into a sedimentary rock. Now, what do you notice about this sedimentary rock? It's nice and flat. It's a layer. What's going to happen on top of that sedimentary rock? After, let's say it's sitting there for a couple million years, what's going to happen after a couple million years to that pink sedimentary rock? Huh? Did you say it's going to turn purple? It might. But what might also happen to it? Does it just sit there, nothing ever happens to it again? Yeah. Well, it's still going to get flattened out, but what's going to happen? It's just like next. Okay, weathering will happen. Okay. And then what will happen after weathering will happen to it? Erosion. And then what happens on top of it? More layers. There we go. So after we've got one rock sitting there, more rocks are going to more sediments are going to get deposited, buried, compacted together. I'm going to skip the squishing together part on top because that will create havoc. But really what happens is another rock layer forms on top of that. Do we get the concept now? What do you think is going to happen next? Probably going to get another one. So as rocks sit around, they don't just they're just not the same for millions of years. Every so often, more rocks are going to get deposited, buried, all that good stuff on top of them. So this is going to go on and on. Now, what do you notice? I'm going to turn my rock sideways so you can look at it. And I think a lot of you, what do you notice about those layers? It's like a sandwich. And what particularly do you notice about that sandwich? I'm gonna, this one is perfect color. I'm just gonna steal this. I'm stealing this one because look at these colors. They were perfect together. What do you notice about these layers? It is a sandwich, but what about it? Are you telling me it's like a sandwich? Horizontal layers. So again, it would have been this way, but I turned it sideways so you can see. Look at those perfect layers. So if you guys don't have a situation that looks like this orange and blue one, go ahead and make that. I'm going to just perfect mine a little bit. So all I'm asking you guys to do is go ahead and make a few layers like a sandwich, but kind of spend a little bit of time making them look a little nice at least. Doesn't have to be like Mr. Losi nice. No, I'm not grading you on your sculpting abilities. But if you can at least make this look somewhat organized. So I just took, if you guys want plastic knives, I forgot to mention they are up here next to the bag. So if you want, come on up and grab yourself. Yes, please be careful. The other thing I should have asked is please avoid mixing the colors as much as possible. I know there's going to be some, but try not to make one giant gray hunk. So again, I'm just asking you guys to go ahead and make yourself a rock sandwich here. Yes, so I do want to point out mine, I did stand mine up just so you guys could see the layers, but yours will be laying flat in front of you. So nice horizontal flat layers. Oh, no, because I get real into it. Yeah. Do we have our layer sandwiches yet? Oh, we gotta wait for a big one. What's this called? When there is layers of rock. Who remembers what that's called? This might not have even caught it last week or 2 weeks ago, and that was a while ago. If you remember from the reading, the study of strata, these are rock layers. So right here, these rock layers are also called strata. So while you wanted to call it a sandwich, let's call this strata, rock layers. I know sandwich probably works better. So I'm looking around, I'm seeing everybody's your models. So that's what the okay would have been for, is I would have walked around and said, okay, yours is good, now draw it. How can we represent this in a drawing? Layers. I do want, okay, so a bunch of lines, kind of. I do want you to take your minute to make this look a little bit more drawn out really nicely. So instead of just lines, we're going to do like boxes stacked on top of each other. So your lines would have worked, but I do want to just make it a bunch of boxes on top. And just to distinguish two different colors, I'm just going to go ahead and shade in every other one. So just like I have the pink and green, I'm going to do some blue and white rocks here. So I think this name, Principle of Original Horizontality, is a fancy way of saying the rocks are originally horizontal. So the rocks start off in these perfect horizontal layers. Now, what are some things that could happen to these horizontal layers? Nope, that was the actual question. So now that we've got these perfect horizontal layers, what are some things that could happen to my rock layers? Okay, let me point out one thing. So you see how this set of rock layers fits in my hand? This is not to scale. This is talking about the layers that cover the whole area. So the rocks that go from Buffalo down to Jamestown, those are the layers I'm talking about. So I'm not actually talking about a rock that is that can fit in my hand. I'm talking about rocks that cover the whole state practically. So what's one thing or two things that could happen to these rocks? What's your thought process back there? Sam, what were you thinking? Cutting. Is there any time that rocks could get cut or broken? What could break or cut entire layers that cover a whole state? Okay, so that's one thing I wanted to make sure you didn't think. So one thing is that we can't break whole layers of rocks with weathering and erosion type movements. It's not strong enough. They're not big enough. We're talking not just rocks the size of your house, we're talking about rocks the size of the state. Nothing can move that bedrock that's just an agent of erosion. What is the strong enough force that we've talked about moving rocks as big as our state? Earthquakes, tectonic plate movement. So these plates that are big enough to cover all of New York or all of Western New York or some huge amounts of rocks, the only thing strong enough to move these rocks would be plate tectonics. So these rocks can get broken like a fault. They can also get tilted. What would cause tilting of rocks? Here's some rock layers there. I just made my fingers into rock layers. Huh? I think you mean convergent plate boundaries where they come together. When two plates come together, we're going to take those horizontal layers and tilt them. So I could take horizontal layers, they're going to squish together and make a mountain. So these rocks might get tilted. Other things that can happen with plate tectonics, not only do the plates get tilted, but they can also do what's called getting folded. When two plates come together, sorry, paper's not moving. When two plates come together, they can fold on top of each other. What the principle of original horizontality tells you, so guys, I see you playing with your Play-Doh, but are you listening too?
Yes.
Principle of original horizontality tells you they were originally horizontal. Whatever happened to them is younger than the rocks. Like, could you tilt rocks that aren't there? Can you tilt a rock that's not in front of you? You tilt empty space? No, there's nothing there to tilt. The rocks have to be there to get tilted. The rocks have to be there to get broken. So this helps us tell us who's older and who's younger. because the rocks had to be there to get broken or tilted or folded. Let's move on to principle of superposition. So keep your rocks all stacked up nicely. Oh shoot, you guys haven't dismantled them, have you?
Oh, yeah.
Okay, put them back together the way you had them.
Gotta do all that work.
Well, I don't feel like I ever gave you the directions to dismantle them, but you're right, I didn't. So just quickly put together your strata, your layered rocks. Hey, since you're rebuilding them right now, where's the oldest layer going to go? How is the oldest on the bottom? Like, what do you mean it's the oldest? Like, when you're building these layers, why is that one automatically the oldest? Because there we go. It's the first one to be put down. Yes, it's going to be on the bottom. You cannot build rock layers starting at the top and working down. Gravity doesn't work that way. So we've got one layer, it's there first. That's why it's the oldest. This one's going to be younger because it's on top of it. That green layer is going to be older than this pink layer that I'm putting on. But here's another question. I've got two pink layers now. I'll spread them out just so you can see them a little bit. I've got two pink layers. Are they the same age? So does everybody agree that they're not the same age? Why are they not the same age? You're right. Because they came at different times. That bottom pink layer is way older than the top pink layer. So that's one thing to point out. Just because the rocks look the same does not mean they're the same age. You do have to look at the order that they are. Oldest on bottom, youngest on the top. So you should already have your sandwich stacked up there, your strata sandwich, your rock layers. What can we do for the next box to draw principle of superposition? What do we got to do to our drawing or your model to demonstrate this? So let's hear from some other people around the room. How can we demonstrate principle of superposition? Oldest on the bottom, youngest on the top. What do we got to do to our model or do to our drawing to demonstrate this part? Well, you guys already told me. I do know you know this. Hey, Olivia, how'd you know that those pink layers were different ages? What did you say when I had they came at different times? What would you want me to do? Let me turn it this way. If you have this, what do I need to do to demonstrate principle of superposition? Here's the ground, by the way. My hand is the ground. Or would you like me to do my hand is the ground this? What? Yes, I'm holding all of you up. I feel like that might be the truth. What do I need to do to this model so that you know that I know you know principle of superposition? Alex, which one's the oldest? How'd you know that? So what do I need to do to show that on here? You told me, you just told me. You know it. Let's just add a label. How about that? Let's draw the same thing. You knew that. So draw the exact same picture that you drew for the last one. And what do we need to do to our drawing? We just need to add a label. I'm going to add a label telling me this is the oldest. And this is the youngest. Hey, and now can I specifically tell you, do not dismantle your strata.
Don't dismantle it. Just do it.
How about this? Can you guys show me faulted strata? So you have your strata, your sandwich, but we need to break the strata, so the layers. We're not going to take it apart bit by bit. We need to break the layers, just like breaking a sandwich. Sam, do you eat a whole sandwich? Or do you ever break a sandwich? Oh, you just eat a big whole sandwich.
Oh, dang, if I got Whole thing.
So you don't break it ever?
So I just.
Oh, you what?
But
You
if
don't
it
eat
was
a whole foot long like this
a
and just
small
house it?
cut half, okay? Yeah, technically.
Okay.
If I had a choice, I'd just.
Any of you people a little more dainty than Sam and Trenton back there, do you guys cut your sandwiches ever? Okay, when you cut a sandwich, you are faulting your sandwich, you are breaking it. So that's what we're going to do to our strata. So we're just gonna gently, trying to avoid mixing the colors as much as possible, fault our strata. Thanks, Mr. D, for the delivery. So guys, again, what's strong enough to break the whole strata like that? Tectonic plates. So when these tectonic plates break the strata, it cuts them. And what happens, you guys remember Africa and South America and Pangea? Remember how Africa and South America fit together like a puzzle piece? Well, this is part of what Alfred Wegener noticed. He was over here in South America and he's like, look, green, pink, green, pink. Then he went over to Africa and he's like, look, green, pink, green, pink. He's like, I wonder if those green, pink layers would match up if I push them back together. And that's exactly what he found, that the rock layers matched up in age and type. So how should we represent this in our drawings? What do we got to do to show that in our drawing?
Should do compared.
You could cut them zigzag. I'm not good at cutting zigzag, so I'm going to cut a nice straight. And my layers are going to be the exact same layers I've been working with this whole time. Just cut apart. So I now have some faulted strata. I've got those same rock layers just broken in half. What are we missing for intrusion and extrusion? What do we need to add to our drawings or our models here? A potato, is that what you just said? That's not it. Go ahead and read intrusion and extrusion, see what we're missing. Magma, I'm gonna deliver you some magma right now.
It's not great.
Yeah, well, I was going to be black, but somebody stole my black, so.
Right, it's not black either.
It could be when it pulls apart.
Right, but that makes no sense. Right. It's called imagination. Yeah, okay, so.
Here's some magma for you. Yeah, imagination is the word for today. Did everybody get some magma? Yes, you guys are working with green magma. I got some black magma up here. Because you stole my black. You know, that's enough out of you. So we're going to be doing intrusion and extrusion. So let's start with an intrusion. Hot magma squeezes into cracks and zones of weakness inside. Go ahead and show me some intrusions in your models of Play-Doh there. Think about this. Where does the Play-Doh come from? Where does it go?
Right, comes from the factory.
Hey, not the Play-Doh itself.
And it goes to Walmart.
You need one more. It's literally perfect. Mine is one today.
Hey, let me get some. That is where you want. It comes from where? Yeah. So show them. That good? No.
Yeah, that's good. Where's it coming from? Never mind. up from the bottom. Now, there's one thing missing about yours. So this is really good, except for reread intrusion. There's one thing that's me, and it
You just paid
is inside. So we'll see how yours meets. There's a way to fix that.
That's really excited.
So now it's nicely buried inside, yeah, inside. Ooh, why did I just think I was tripping over a dog? It's just a backpack.
The dog.
I literally just got nervous that I tripped over or stepped on a dog, but it's just Brooklyn's backpack.
Dog.
I've been home for, well, actually, I haven't been home for a week, but there's dogs in my life. If that's normally what I'm tripping over, are dogs. Okay, walked around, I saw a lot of good ones. The biggest thing I saw was this. Where, and again, I'll turn it sideways. So again, the ground is here. Or the inside of the earth. This is one thing I saw a lot of. I saw lava coming up through the layers and exploding like a volcano. There was one thing wrong with this. What's wrong with this scenario? What are you getting at?
It stays inside.
So it stays inside. It's an intrusion, and an intrusion means that this lava or this magma does not make it to the Earth's surface. So one very simple solution to this model was I squished over my magma and added a new layer on top. So if you can see what I got going on here, except for my Play-Doh is definitely drying out. What I got going on is I got my green layer, pink layer, green layer, pink layer, but this magma has squeezed up through my top pink and green layers. It has not made it to the surface. This is pretty much the drawing I would like you to make. And here, let's go ahead and take a minute to draw this. So I'm going to stick with my same original layers. And then I'm going to add my lava that came up and squeezed through. You know what? I'm going to deliver you guys all some red. So you can draw your lava in red. I think I'm going to be able to deliver some red. Yeah, colored pencils are back there. Not sure where my reds are. But so we're going to deliver some red for you to draw your lava in red. But while we're doing that, let's talk about this. What is lava? What is magma? It's hot. It's hot, melted rock. When I say melted, it's liquid. It pours out like a water. It's hot, hot liquid. What do you think that hot liquid is doing to the rocks that it's touching? Now, do you think it's going to melt them? Here's where I'd like to refer. Yeah, it's going to heat them up. It's like when we talked about s'mores. Do you know? Contact metamorphism. So let's just go through it for those of you who didn't remember it that quickly. So remember your hot flaming marshmallow that you might make when you're making a s'more. That's what my kid does. So we take a hot flaming marshmallow and you put it on the chocolate. What happens to the chocolate? Now, does it melt that chocolate? It just heats it up. It's not hot enough. It loses some energy from going from the hot flaming marshmallow to your chocolate. It's not hot enough to melt your chocolate. It'll make it ooey gooey. It'll change it, but it won't melt it. And if you remember, metamorphic rocks are the rocks that are changed by heat and or pressure. So the Regents does one thing to demonstrate this as an intrusion, and it shows that contact metamorphism. What's missing from our drawing are what I call whiskers, but they're really representing contact metamorphism. So what I need you to do along your entire intrusion is to add these little, little hair-like things. I call them whiskers, but that's demonstrating contact metamorphism. So see how there's contact metamorphism around this entire picture? Sam, guys, you with me? So see how I added those whiskers around the whole intrusion? That's telling you that all of these rocks were there and the intrusion basically came through and burned them. So again, the contact metamorphism shows that those rocks were changed by the hot lava. Let's do one more, which is perfect. We're just about out of time. We need to do an extrusion. How's an extrusion different? Take off the top layer. An extrusion makes it to the surface. So again, we can draw that exact same picture. We're going to have our different layers. And this time we're going to draw our lava, but it's going to make it to the surface. So same blob of lava, but it makes it to the surface. Do we need to add any contact metamorphism to this drawing? Guys, it's an actual question. Do we need to add any contact metamorphism? When does contact metamorphism happen? When magma touches rock. So are there any places magma's touching rock? Okay, so there is some places. So is magma touching rock down here? Is this pink touching any rocks? Right here. Right here. Yeah, it's touching these rocks. So we need to add the contact metamorphism all down here because it's touching all those rocks around it. Is it touching any more rocks? Yeah, it's touching some right here. How about now? Is it touching any other rocks? Right now, is it touching anything? Nope. So we got it touching all these layers and the bottom of the extrusion. Do we need any of those whiskers on the top? Why not? There's no rock there to touch. So it's not going to change something that's not there. So now after maybe 100 years, what's going to happen? Or even quicker than 100 years, what's going to happen to that hot lava? It's going to cool. It's going to harden. It's just going to become rock. Maybe granite, maybe basalt, maybe obsidian, whatever. It's going to become a hard, normal, everyday rock. So then remember what happens maybe another 1,000,000 years? We might get another rock layer on top. After 1,000,000 or so years with this new rock layer, do we have to add the whiskers to this now that we have a new layer on top? Why not, Alex? It's already cooled. It's already hardened. So there's no more whiskers, no more contact metamorphism because it's already cooled off. So this is still considered an extrusion, even though it's covered up because it's bald on top, no whiskers. So the regents will often ask you, is this an intrusion or is this an extrusion? And the way to tell is where the whiskers are. If it's covered in whiskers all the way around, it's an intrusion. If it's bald on the top of the intrusion or on the top of the lava, then it's an extrusion. Okay, so we're just about done. I am going to give you homework. If you turn over to page 17, there are 4 questions. Guys, I'm literally giving you 4 questions for homework. I would like you to really put in effort on these 4 homework questions. Don't just guess, read through them, check out the notes we just did. Actually, now that I'm looking at this, you can skip number 1. Sir, we did not learn number 1. You can skip number 1. So go ahead and give those a whirl. Put your Play-Doh away too, by the way. Make sure it gets back in the right containers. The